Hello, and welcome to the next section in the exploration of space. In the last section, we looked at ICBMs and discovered why they're different from some space vehicles because they only spend a short time in space. We also looked at some of the history of ICBMs and the current status of nuclear weapons on our planet. In this lesson, we'll learn the basics of space vehicle re-entry motion, how a space vehicle re-enters a planet's atmosphere, and the various trade-offs for re-entry design and re-entry motion. This material is challenging because we must delicately balance three often competing requirements for re-entry vehicles: deceleration, heat, and accuracy of landing. You can see here the Apollo re-entry capsule that was one of the earliest re-entry vehicles for astronauts. Without a safe re-entry, a mission would fail, so it's an important part of every crewed space mission. All space mission planning begins with a set of requirements to achieve mission objectives. The re-entry phase of a mission is no different. You can imagine being an astronaut racing through space at phenomenal speeds, yet facing the challenge of hitting the exact angle and speed for a safe re-entry and landing. The three engineering trade-offs for mission design are deceleration, or slowing down, the heat of the spacecraft during re-entry, and the accuracy of the landing or impact. We're going to discuss all three in detail, so let's begin with deceleration. A safe amount of deceleration is determined by a vehicle's structure and payload. The difference between too much or too little deceleration can mean a successful re-entry or a disaster. Let's talk about too much deceleration first. The goal is to limit the maximum deceleration, or G's, the vehicle can withstand. Okay, but what's a G? Well, 1 G is the gravitational acceleration at Earth's surface, which is 9.81 meters per second, or 32 feet per second. It's the amount of downward pull on us while we're on Earth's surface. If we have 2 G's, then we feel twice our weight pulling us down. When subjected to enough G's, even steel and aluminum can crumple like paper. Fortunately, the structural G limits for a well-designed vehicle can be high, perhaps hundreds of G's. But a fragile human payload would be crushed to death long before reaching that level. Well-conditioned humans can withstand a maximum deceleration of about 12 G's, which is about 12 times their weight for only a few minutes at a time. Try to imagine 11 other people with your same weight all stacked on top of you. You'd be lucky to breathe. Just as a chain is only as strong as its weakest link, the maximum deceleration a vehicle experiences during re-entry must be low enough to prevent damage or injury to the weakest part of the vehicle, which is usually the human payload. Too little deceleration can also cause serious problems. Similar to a rock skipping off a pond, a space vehicle that doesn't slow down enough may bounce off the atmosphere and back into the cold emptiness of space. This rock skipping is a really good example, so let's think about it a moment longer. When the wind is calm and a pond surface is smooth, the conditions for skipping a rock across the pond are excellent. But we have to take careful aim because we want the stone to hit the water's surface at an exact angle and speed. Well, astronauts face a similar challenge. For re-entry vehicles, Earth's atmosphere is dense and fluid at orbital velocities, and for that reason, it's not much different from a rock skipping on the surface of a pond. So the astronauts and mission planners must make the re-entry vehicle hit the atmosphere at the exact angle and speed for a safe landing. If the vehicle hits too steeply or too fast, they risk a fiery end to the mission. And if the angle is too shallow, the vehicle could skip off the atmosphere and back into space. And the new orbit would not be a good one to try re-entering again. Okay, I think you should have a pretty good idea of how we handle the deceleration of a space vehicle. So let's move on to the vehicle's heating. If you've ever seen the fiery trail of a meteor streaking across the night sky, then you know that re-entry gets hot. This intense heat is the result of friction between the speeding meteor and the air. How hot can something get during re-entry? To find out, we need to think about the energies involved. The Space Shuttle in orbit has a mass of 100,000 kilograms or 220,000 pounds, an orbital velocity of 7,700 meters per second or 17,225 miles per hour, and an altitude of 300 kilometers or 186 miles. Those are a lot of numbers to throw at you, but think about it this way. The shuttle has enough energy during re-entry to heat the average home in Colorado for 41 years. Now let's review some material we learned in Chapter 5. We said that kinetic energy was energy from velocity, and potential energy was energy based on a spacecraft's distance from Earth's center. So we know an object's total mechanical energy depends on its kinetic energy, or energy of motion, and its potential energy, or energy of position. The shuttle has kinetic energy because of its speed of 7,700 meters per second and potential energy because of its altitude at 300 kilometers. It must lose all this energy in only 1/2 hour during re-entry to come to a full stop on the runway at a shuttle landing site. So re-entry tends to be a hot topic among astronauts. That's a lot of energy to lose in such a short time. Remember that earlier we said all of the energy converts to heat from friction between the atmosphere and the vehicle. This heat makes the shuttle's leading edge surfaces reach temperatures over 1,400 degrees centigrade or 2,600 degrees Fahrenheit. So the challenge is to design the re-entry trajectory to minimize the heat and to design a vehicle to withstand these high temperatures. When analyzing re-entry heating, we must consider several issues. The total heating is the amount of heat generated based on the re-entry vehicle's energy. And the peak heating rate is the maximum rate at which the potential and kinetic energy convert to heat. A re-entry vehicle's surface material must withstand the total heat and the peak heating rate to survive. We've already discussed two of the requirements for re-entry design, deceleration and heat. Now we're going to move on to accuracy. Why would accuracy be a driving design consideration in some missions, but not in others? Any thoughts? Well, let's consider 3 types of missions and think about their accuracy requirements: ICBMs, Apollo, and the Space Shuttle. If you think back to the last chapter on ICBMs, then you know that a very high degree of accuracy is required for a successful mission. You can see the Peacekeeper ICBM on this slide, which is an example of a highly accurate missile. Now let's consider the early Apollo re-entry capsules, similar to the one shown here. The accuracy requirements allowed for splashdown in a large area in the Pacific Ocean. But helicopters and ships waited close by to retrieve the astronauts quickly. Because of the human payload on board, the capsule re-entry angle had to be shallow to minimize the deceleration, and that caused a large landing area. The Space Shuttle landing runway shown here is only 91 meters or 300 feet wide. But after descending through the high heat region, the shuttle is very maneuverable, so the astronauts can steer it to a pinpoint landing on the runway. In all cases, designers adjust the trajectory and vehicle shape to match the accuracy requirements. As you can see from all these requirements, a re-entry vehicle must walk a tightrope between being squashed by too much deceleration and skipping into space with too little deceleration, between burning up or freezing, and between accurately hitting or missing the target. This tightrope is actually a 3-dimensional re-entry corridor through which a re-entry vehicle must pass to avoid skipping out or burning up. The size of the corridor depends on the 3 competing constraints, which we know are deceleration, heating, and accuracy. Let's look at this diagram and restate this idea of a re-entry corridor. If the vehicle goes below the lower boundary or undershoots, it will experience too much air drag, slow down too rapidly, and heat up too quickly. On the other hand, if the vehicle re-enters above the upper boundary or overshoots, it won't experience enough drag and may skip off the atmosphere back into space. Now here's a scary thought for you. If the designers aren't careful, these competing requirements may lead to a re-entry corridor that's too narrow for the vehicle to steer through. Whereas these three requirements determine the re-entry corridor size, the re-entry vehicle's control system determines its ability to steer through the corridor. In this chapter, we'll concentrate on describing the effects of the corridor size. We'll discuss limits on the control system in a later chapter. Before we get to the new material, let's look at an example to reinforce what you already know. Imagine a meteor speeding through space until it encounters Earth's atmosphere at more than 8 kilometers per second. In the upper reaches of the atmosphere, the air is very thin, so it has little drag to slow it down. As the meteor penetrates deeper into the atmosphere, the drag force builds rapidly, causing it to slow down. The meteor's velocity stays nearly constant for the first 10 seconds in the thin air, but then changes during the next 10 seconds when it loses almost 90% of its velocity in the denser atmosphere. Unlike the meteor, defining a trajectory for a valuable re-entry vehicle means we have to trade deceleration, heating, and accuracy to calculate a safe re-entry. Now you've got the basics of re-entry trade-offs, so let's move on. To begin analyzing re-entry motion, we need a coordinate system. Think back to Chapter 4 when we discussed the motion analysis process, where our first step was to define a coordinate system. For re-entry motion, we still need an inertial reference frame so we can apply Newton's laws. We create a re-entry coordinate system that provides a way to track where a re-entry vehicle travels. Keep this mission analysis process checklist in mind because all of the checkpoints can be used during this section on re-entry motion. To make things easy, we place the origin of the re-entry coordinate system at the vehicle's center of mass at the start of re-entry. We then analyze the motion using this fixed center. The basic or fundamental plane is the vehicle's orbital plane. Within this plane, we pick a main direction that points down to Earth's center. As a rule, the axis that points down is the z direction. Then we define the direction along the local horizontal in the direction of motion as the x direction. The local horizontal is a line tangent to the orbit and perpendicular to the local vertical. The local vertical is a line from the vehicle's center of mass to Earth's center. Because the re-entry vehicle never travels very far left or right of its orbital plane, we don't use the third axis that would be perpendicular to the fundamental plane. That's a lot of information to throw at you, so follow along with this diagram as we restate the concepts. The re-entry flight path angle is the angle between the local horizontal labeled x and the velocity vector labeled v. Vectors are quantities that have both a magnitude and a direction. A re-entry flight path angle below the horizon is negative and means the vehicle is diving toward the ground. A re-entry flight path angle above the horizon or climbing is positive. Re-entry vehicles almost never have a positive re-entry angle. If you remember the key topics from this and earlier chapters, you can probably name some of the forces that are acting on a vehicle during re-entry. We'll look at this diagram to see how well you do. The forces labeled F in this figure, which the spacecraft must withstand, are drag, lift, gravity, and other forces. In the case of drag, the arrow points behind the spacecraft. The lift arrow points up from the spacecraft, while the gravity arrow points down toward Earth. By using the local horizontal reference line shown on the figure, you can see the flight path angle. Now, is the flight path angle positive or negative? The correct answer is negative because the angle is below the local horizontal and the vehicle is diving toward the ground. Okay, keep following the diagram and let's go back again to the map or motion analysis process. One of the steps is to make a complicated equation easier by thinking of some simplifying assumptions. First, we assume that the re-entry vehicle is a point mass instead of a complicated aerospace vehicle. Then we say drag is the main force, which means that all other forces, including lift and gravity, are insignificant. And we'll see why this assumption is good later. Lift is a force at a right angle to the direction of motion as a result of air moving over an object's surface. The motion analysis approach for re-entry vehicles requires us to develop an equation of motion and examine how different parameters affect it. But to keep this complex topic simple, we can begin analyzing the motion by reconsidering the meteor example that we mentioned earlier. So, the drag force on a meteor or a space vehicle depends on several things. But one fact is that the drag force is more than 160 times larger than the gravity force. What factors do you think would affect the force of drag on the meteor or vehicle? If you remember the pieces you've already learned, you'll know the answer. You'd be right if you said the force of drag depends on its velocity, how big it is, or its cross-sectional area, its mass, how dense the air is, and its drag coefficient, or how streamlined it is. We describe how streamlined a vehicle is by using a unique property of vehicle shape called the coefficient of drag. Engineers compute and check a vehicle's coefficient of drag using wind tunnels similar to the one on this slide. Drag pushes backward on the vehicle as it re-enters. So acceleration in this case is really deceleration because it slows the vehicle. Using Newton's second law of motion, if we know the mass, we can relate the force of drag to the acceleration it causes on the vehicle. A handy value for rocket scientists is the ballistic coefficient, or BC, that we define as a measure of air drag. The higher the number, the less drag the vehicle experiences. So, for flying through the air, the bigger the ballistic coefficient value, the better. Let's talk about deceleration by describing Jerry, our daring rocket scientist, and a sack of potatoes falling out of an airplane as an example. The amount of deceleration an object experiences while traveling through the atmosphere relates inversely to the object's ballistic coefficient. An inverse relationship between two things means that when one goes up, the other goes down. The same principle applies to deceleration and ballistic coefficient, or BC. Okay, let's see what BC really represents. Suppose Jerry weighs 150 pounds, which means he has a mass of 60 kilograms, and a 60-kilogram sack of potatoes fall out of an airplane at the same time. You should be thinking that the sack and Jerry have the same mass and the same initial velocity. Along with assuming the same mass and velocity, we also assume that they have the same cross-sectional area and drag coefficient. This means they have the same BC. Thus, the drag force on each is the same, and they fall at the same rate. When Jerry opens his parachute, he slows much faster than the sack of potatoes. But why? What happens to his BC? Let's think about this point by point. Jerry's mass stays the same, but when his chute opens, his cross-sectional area and drag coefficient increase dramatically. And when that happens, his BC goes down, making his descent rate slower than the potato sack's descent. Dives into the atmosphere. Its deceleration builds quickly, generating so much heat that most meteors burn up long before they hit Earth's surface. Okay, because the concepts in this section are challenging, let's go back over an important point. An object entering a planet's atmosphere has tremendous kinetic energy because of its speed and potential energy because of its height above the surface. Its energy turns to heat when it hits air molecules. If you've ever tried to stop your bicycle by dragging the soles of your shoes on the ground, you've experienced turning speed into heat. Because of the extremely high energies involved with re-entry, the amount of heat on meteors is so great that most burn up long before they hit Earth's surface. Let's take the heat concept into the real world as we look at this slide. You can see the final phase of the MUSES-C mission, which had a small re-entry capsule with the asteroid sample inside. It re-entered Earth's atmosphere at a velocity of over 12 kilometers per second. The maximum heating rate of the capsule during re-entry was 10 times higher than that of the space shuttle and several times higher than the Apollo recovery modules. Therefore, leading-edge technology was necessary to develop the heat shield. After being fully decelerated by the atmosphere, the capsule deployed a parachute for a soft landing. The capsule, which was located by a beacon signal it sent out, was then retrieved. so you can identify deceleration, heat, and accuracy in action with this modern example. Answer the questions on this slide. If you have the answers correct, you're ready to move on to the next section. But first, we'll summarize this section. We've just learned the basics of re-entry motion. We know about 3 competing requirements for re-entry design: deceleration, heating, and accuracy. We understand the re-entry coordinate system and how a vehicle's ballistic coefficient affects its deceleration. We've spent much of the course trying to understand orbits, maneuvering between them, getting to them, and returning from them. The next phase will focus on space missions and how to develop the hardware needed in orbit to complete them.